In this video, we are going to review 6 questions related to the material covered in the chapter 1. First question. Which orbital overlap results in formation of an antibonding or sigma star orbital? So the orbital should be sigma orbital and it should be antibonding. Sigma orbital has electron density that is along the internuclear axis. It's between the two atomic nuclei if it is bonding or sigma orbital, and it is outside the two nuclei along the axis but past the two nuclei if it's antibonding orbital. When we consider the 4 possible answers, we can see that answers A, B, and D will result in formation of a sigma orbital. Answer C has 2 orbitals, 2 atomic p orbitals that are at 90 degrees to each other, and that overlap will not result in formation of chemical bond. In case of A, B, and D, the 2 atomic orbitals are aligned in such a way that they are along the internuclear axis, and those will be sigma orbitals. In case A, we can see the 2 atomic orbitals that are overlapping are out of phase. They are shaded differently. We indicate phase of the lobe of the orbital either by signs plus or minus, or by color, different colors, or different shades. In this case, it's different shades. Since they are differently shaded, they are out of phase, and that's going to be sigma star or antibonding orbital. So that's correct answer. Answers B and D would result in formation of bonding sigma orbital. Next question, which of the following does not appear on an energy diagram for formation of methane? Only physical processes will appear on energy diagram because physical processes involve change in energy. So promotion requires energy for promotion of electron from S energy level sublevel to P energy sublevel. Also CH bond formation involves release of a large amount of energy, so that's also going to appear on energy diagram. Answer C, hybridization will not appear on energy diagram because hybridization is only a mathematical operation. It is there to fix valence bond theory. Without that mathematical operation, valence bond theory could not explain bonding in methane or in general in hydrocarbons. And so this is simply mathematical trick, mathematical operation to fix a broken theory. So correct answer is C. Of course, D, all of the above are shown on the energy diagram, is not correct. And question number 3. What is hybridization of carbon in the molecule below? We have carbon attached to nitrogen by a double bond. A double bond involves a sigma and a pi orbital. A pi orbital is formed by the overlap of atomic p orbitals, which means that one orbital on carbon atom will not be hybridized. There are 4 atomic orbitals on carbon that are involved in bonding. 1 is not hybridized. If remaining 3 are hybridized, that means sp2 hybrid. Hybrid of 3 atomic orbitals, 1s and 2p orbitals. Next question is question number 4. Which of the following molecules exhibit a dipole moment? So you should go through each of these 4 molecules, 1 through 4, and find out which exhibits dipole moment. And the best thing to do is to draw their structural formulas. So perspective drawings or three-dimensional arrangement. So first one, carbon tetrachloride. That one does not exhibit dipole moment. It's tetrahedral. It does have polar bonds, individual polar bonds, but all 4 polar bonds are identical, and their individual dipole moments cancel each other out. So overall, molecule does not have a net dipole moment, which means molecule 1 is nonpolar. Molecule number 2 has 3 identical substituents on carbon, 3 hydrogens and 1 chlorine. 3 carbon-hydrogen bonds are polar, with negative end of the dipole being on the carbon. And carbon-chlorine bond is polar, but in this case negative end of the dipole is on the chlorine, while positive is on the carbon. Which means that these individual bond dipoles obviously cannot cancel each other out, and overall molecule has to be polar. So molecule number 2 is polar. Molecule number 3 that will be hydroxylamine, is obviously very unsymmetrical with lots of individual bond dipoles and lots of individual dipoles due to free electron pairs. So obviously they cannot cancel each other out, and that has to be a polar molecule. So molecule 3 is also polar. Molecule 4 is aluminum trichloride, or just aluminum chloride. It's trigonal planar with 3 identical substituents on aluminum. And so even though each of the individual bonds is polar and is a dipole that way, 3 dipoles cancel each other out. So overall molecule is not polar. So in conclusion, only molecules 2 and 3 are polar, which means that B is the correct answer. The free electron pairs on oxygen in acetaldehyde are in what type of orbital? So free electron pairs will be in hybrid orbital if atom is hybridized, and only halogens are not hybridized. So in case of oxygen, we need to figure out hybridization of oxygen, and hybridization is sp2 because oxygen has 1 pi bond. So free electron pairs will be in sp2 hybrid orbital. Draw a Lewis structure of methyl isocyanate. To help us with drawing Lewis structure of this compound, we have here a condensed formula. From that formula we can see that there is methyl group, CH3 group present, then it is attached to nitrogen, which in turn is attached to second carbon atom, and finally that carbon atom is attached to oxygen. We can use that information and also knowledge that no atom can exceed octet to draw Lewis structure. You may want to pause video here and examine it. Also, you may want to draw Lewis structure on your own and then compare it with this answer. And this completes chapter 1 exercises.